Okay, welcome everybody to a very special event, which is part of the remote experience for young engineers and scientists, better known as REYES. Today's talk is also a joint colloquium with the physics department. Physics department, I'm also a staff scientist at Jefferson Lab and the co-chair of the REYES program. As I already mentioned, this is a program that is being hosted by Old Dominion University. REYES is made possible by a dedicated team of ODU faculty and staff. Let me walk you through their names. Some of them might be already familiar to you, and if not, they will become increasingly familiar throughout the year. We have Orlando Ayala, who's an ODU faculty, Alan Mecca, ODU faculty as well, Maite Wilson, Senior Administrative Assistant, Christopher Fleming, Assistant Vice President for Enrollment, Giovanna Gennard, the other co-chair of the REYES program, the Assistant Vice President for Strategic Communication, Oscar Gonzalez, who's an ODU faculty as well as ODU chair, Miguel Ramlanchan, Assistant Vice President for Technology, and Sherry DiBari, PR specialist. This event would have been made possible with their hard work. REYES is an interdisciplinary program aimed to meet various different goals. Primarily, we want to inspire the future generation of STEM age experts. We obviously want to showcase our the goods of our community, but we want to build a broader collaborations locally as well as internationally. We want to provide as much free STEM age-based content to those interested, and we want to give you some much needed relief in this current climate. The REYES program is just one of the examples that demonstrate ODU's commitment to creating pathways for students that increase participation in science, technology, engineering, mathematics, and healthcare fields, and increasing engagement with our community. REYES started in June of 2020, shortly after the beginning of the pandemic. And although we're located in Virginia, we're able to reach an international audience of more than 3,300 participants from across the country, as well as the rest of the world. We extend our reach extends to 114 other countries across the world, with a substantial presence from Mexico, where our today's speaker is from. This past summer, we hosted over 80 STEM-based virtual lectures and activities, including panels, talks, etc. And in addition to having these series hosted live, all the sessions are recorded and available for free viewing on our website, odu.edu/REYES. If you miss any of the talks, you can go swim through our repository of talks. In total, we've had close to 20,000 views just from the summer alone. And what I want to present to you is an exciting extension of this program, where we have some selected key speakers for the fall, and I will leave today's speaker for last. The first talk is going to be by Jamie Sahorian, and that's going to take place in October 16th, who will be talking to us about it. I should mention Jamie Sahorian. He's the lead senior scientist in Butterfly Network. He's also an ODU alum. So he will be both telling us about great technology that he's been able to develop, and tell us a little bit about his story. In particular, he's going to be telling us about the Butterfly IQ ultrasound probe and the decisions that led him to join a revolutionary startup. The speaker after Jamie is going to be Stuart Henderson, who will be speaking November 9th. He is the director of the Thomas Jefferson National Accelerator Facility, also known as Jefferson Lab. He's also a distinguished CBATH professor at Old Dominion University. He will be telling us about big science, discovery at the biggest and smallest scales with big instruments and big teams. So mark that in your calendar. And the last speaker of the series is going to be an astronaut. We haven't pinned down the date, and so we're leaving this mysterious announcement for you to come back and look for it. We will be announcing this shortly, so please stay tuned. And finally, this brings me to today's speaker, Saul Ramos Sanchez. Saul Ramos Sanchez is a researcher at UNAM. UNAM is the Universidad Nacional Autónoma de Mexico, which is the largest university of the Americas. He's a researcher specializing in string theory and the study of elementary particle physics and cosmology. He obtained his doctorate in Bonn. He has published over 40 research articles, dozens of popular articles, a textbook on the theory of relativity. He seeks to establish a connection between string theory and experiments. He also is an outstanding advocate of aspiring scientists. He has been partly responsible for the program that allows students in Mexico to come to Jefferson Lab, as well as other institutes across the world. And it was through this through this program that we got to know each other. So it's a great pleasure to have Saul join us today to give this joint talk of REYES and the Physics Colloquium. I should mention right before before giving him the platform that you're free to ask questions and raise your hands. You can either do this by the chat or just raise your hand and we can address these questions at the end of the talk. So with that, I'm going to turn it over to Saul. So I'm going to stop sharing. Please, Saul, go ahead and share your screen.
Yeah, thank you. Thank you very much for this nice introduction. Well, yep. Thank you, Raul. Thank you very much for this very nice introduction. And thank you to all the REYES team. I included Giovanna, Cristina, Karen, Christian, and of course, Raul Briceño, for giving me this opportunity to talk to you, to talk to everybody. Thank you as well to you for being here, for trying to understand what the string theory has led to in the last, say, 30 years since its startings. So I will go to the main questions that I guess are interesting to answer in nature, in physics, and I will arrive to the description of the general features of string theory for you. And if you have any question, please let us know. As Raul said, there is the question and answers, the chat, and somebody will tell me what the question you have is, and I will try to answer it as soon as possible. Well, as I was telling, I will go to study the most interesting strings that I know, and they are those that come from string theory, of course. And I will start with the most important question, or one of the most fascinating questions that humankind has ever posed. This is the one. What is the universe made of? Of course, in the last 4,000 years, many people have conceived several possible partial answers, and by using those answers, we have arrived to understand the mysterious working of the universe. And of course, in those discoveries, we have also made use of the possible applications that we are actually abusing of today. For example, now, with the pandemic, we are using cell phones, we're using computers, we're using a bunch of stuff that are useful, of course, and they are just conceived thanks to our discovery of what the universe is made of. So let me just go there. What happened 4,000 years ago? In the ancient Babylonia in the 1800s BC, people thought that the universe, everything was composed of 4 ingredients, 4 basic elements: air, water, fire, and earth. I don't know exactly how it worked, but for many people, it was just simply basic knowledge. There are 4 elements and everything is composed out of them. And this was so popular that it actually lasted until Middle Ages. The beginning of the 1600s, if you wish, or by the end of the 1600s, people were still convinced in the Middle Ages that it was like that, perhaps because church supported this idea, I don't know. But it is actually surprising to me as well, because in those days, many people, including Galileo, of course, were doing experiments. We're in a lot of experiments. There were alchemists like Newton itself, Isaac Newton, who tried just simply to create gold out of different materials, combining different materials with heat, with water, with earth, with air, with everything. And of course, they were just combining stuff and obtaining new stuff, and they were surprised that it was kind of the birth of chemistry. However, the actual birth of chemistry was, say, proposed or pushed forward by Antoine Laurent Lavoisier in the 1700s. Here he is showing one of his experiments where he is showing one of his discoveries, that oxygen is responsible for combustion. It's like the main ingredient for combustion. But that is not the only law that he discovered in nature, the only discovery he made. He also discovered one particular property of physics and chemistry, the principle of conservation. Mass cannot be created nor destroyed, but only transformed. That is what he discovered, and he discovered it thanks to the fact that he could measure things. He started measuring, and his measurements were the most precise of the epoch. That is nice. If you measure, you discover things. Somehow that was one of the main messages that he delivered to the scientific community, but not the only one. Again, beside oxygen and mass conservation, he also discovered that the different materials combined in different, following different rules until performing different processes and arriving to molecules. And these molecules, he started to classify them in order to give kind of an order, in order to discover exactly how the universe works. So he discovered I don't know, many elements that were already somewhere there in the community, but they didn't know exactly what they were. He discovered 2 or 3 new elements as well. He predicted them. And then he started really a chemistry revolution. He started doing or pushing people to perform measurements, to perform experiments in a very controlled fashion. And even though he was killed because he was also a politician, he was a very good scientist, and he was very respected even 1 year after his death. Anyway, what happened after that, after he was dead, is that people started looking at the atoms. They returned to the ancient Greece, and they thought that maybe those ideas of Lavoisier and many other people had to be regarded in the scope of the atomic physics. Dalton appeared, and many other people appeared, of course, in the early 1800s, until Mendeleev put kind of order in all this stuff. And he decided by observation that all the different elements that were discovered so far, about 50 by those days, he discovered like 10 more of them, that they had certain rules to be somehow accommodated according to their properties to combine with each other. Their valences and their masses were crucial for the first periodic table. This is the first periodic table, and we could then answer the question in the 1869. All the universe is made out of these 50 or 60 elements, basic chemical elements. But of course, this is not the end of the story. Today, we know the periodic table. It contains exactly 118 elements with first names, last names, properties, masses, charges, everything. And we know everything of them. Most of them are created in stars, you know, these supernovae, explosions of stars, of all stars, and they are left all over the universe. But some of these elements actually, in this last line, for example, and most of these elements here were invented, created here on Earth in a laboratory. Perhaps also in supernovae they appear, but we don't know. We know that we created them, and there might be many more to come. So we can say the universe is made of 118 elements. Is it? Well, very soon, people started to look into these atoms: lithium, beryllium, boron, etc. All the atoms had a shell of particles that are charged, called electrons, and a nucleus. And funnily enough, the nucleus is not fundamental. It's also composed of additional particles. Here we have a neutral with an N, which is a very heavy neutral particle. We have also in the nucleus a charged particle, the so-called proton. in violet. And we have this small electron, and we put it in different sizes because it turns out that neutrons and protons that build up all the nuclei of all the atoms are very heavy in comparison with the electrons. Of course, having these three ingredients tells us that actually that is all. We have all the materials of the universe. Everything is composed of three particles, and we don't have to look into more. But we do. Actually, 1911, Victor Hess, a physicist interested in astrophysics, of course, noticed that in the surface of the Earth, there was ionizing radiation. And he said, well, why? Where is it coming from? He took a balloon, he flew over 5 kilometers above the surface, and he noticed that this ionizing radiation were particles, many particles that appear more frequently in the heights in his balloon, 5 kilometers over the surface. He observed many more particles, much more radiation than on the surface. And he was surprised. He didn't know why, because he expected that everything could be, I don't know, neutrons, protons, and electrons. That's it. But it was not. There was much, much more. And people started to, well, researchers started to look into it, and they noticed that the reason why they had seen, or Victor has seen, all these particles or this radiation was because many particles are coming from the sun, from other galaxies, or within the galaxy from certain sources that were not identified before. That most of the particles that arrived to the surface were protons, of course, but then when they collided with the surface of our atmosphere, they created a lot of new particles, a bunch of particles that were not neutrons, nor protons, nor electrons. Everybody was fascinated by this. And they started just giving names to all the particles. There was kaon, protons, antiproton, eta, sigma, delta, delta minus, delta plus, lambda, all the alphabet in Greek, in English, in Spanish, in all the languages, many particles. This was called in those days the zoo of cosmic particles. The zoo of cosmic particles was invading the Earth, coming from everywhere, and they had to understand these particles, of course. How to understand them? They come from somewhere, but maybe they are actually already here, but we haven't been able to see them. They started just looking at those particles coming from the cosmos, but of course you need kind of an order. Whenever you see like thousands of animals, you have to conceive an order in order to start understanding whatever is happening in there. And that is what they did, classify them. First of all, after the names, they used their spin to classify them, their charge to classify them. They used as well their masses, lighter or heavier, they had to know, and also their properties to decay. They had the property to decay in certain time that they called the lifetime of a particle. Most of these new particles decayed into lighter particles that were observed here in nature. Electrons, protons, and neutrons were appearing after some decays of those new particles. They had a very short lifetime. Why? Well, with the time, people had many questions, and some fellows imagined that the answer was string theory. This was the idea of Yoshiro Nambu, who received for other reasons the Nobel Prize in 2008. Holger Nielsen, Leonard Susskind, who said, you know, I think that we have that many particles because in a sense, all the particles can be described as a string. If the string is not vibrating, then the particle is very light. Then let's say this is the lightest particle that you can ever imagine. I don't know, a photon that is massless or a neutrino that is very, very light. But if it is oscillating, that this second string, then it has to be a little bit heavier because this vibration is energy and energy is mass according to Einstein. Therefore, this has to be a little bit heavier. And of course, this string at the top that is vibrating a lot, this has to be the heaviest particle. I don't know, like the top quark or something different. It has to be something very heavy, one of those particles. Of course, this is a very nice idea, but like many nice ideas, it didn't work. I will tell you later why it didn't work, but it's fascinating actually why it didn't work and why at the end of the day, even though it didn't work at the beginning, at the end of the day, it works, or maybe it works. We will see. But since it didn't work, at least in the beginning, to describe the zoo of cosmic particles, people started looking at the similarities and they come up with a new idea. The particles that look similar to the protons and neutrons are actually very similar to protons and neutrons. They are composed of so-called colored quarks. These quarks have different colors and they build together in order to build the white color. We have some particles, some hadrons they call them, some hadrons that are built of 2 quarks, and some other hadrons that are built of 3 quarks, like protons and neutrons. They came up with this idea, but you cannot observe these quarks. So how come that they came with this idea? The point is that there are evidences, different evidences that they are there. Their interactions, their lifetimes, their properties to decay tell us exactly that they are composed of quarks and that the quarks are transforming to each other, and that's the reason why they decay into different particles. So we have these hadrons with quarks, composed of quarks, and we have also these left and right marbles that are the leptons. We have the electrons on the right, we know of them since, I don't know, 150 years ago, and muons that we learned of when Victor Hess mounted in his balloon. Well, we had these particles, very nice. How to explain their interactions? That is the next task. First of all, you told me that neutrons and protons are inside the nuclei, and protons have exactly the same charges. They are positively charged. How come that they interact with each other electromagnetically? Of course, they repel each other because they have exactly the same charge, but they live inside the nuclei of all the basic elementary atoms. How come that they live there? I mean, it cannot be. They should repel each other. They shouldn't be there unless there is a force that attach them together. And this is the strong force. The strong nuclear force put the protons together in the nuclei, together also as well with the neutrons. And the reason is that the strong force is actually attaching the quarks that live in the protons and neutrons. So as you saw, let me just go again. Here, as you saw here, basically these are quarks with colors, and they are exchanging some rays. These rays are so-called particles, are particles called gluons, and they are exchanged by the quarks. And they are called gluons because actually they glue together all the quarks. They glue together the quarks that live within a proton. That's the reason why we don't see them freely. They glue together also the quarks that live within the neutrons, and they glue together also the quarks across protons and neutrons within the nuclei. This is a strong force, and this is called strong because it is stronger than the repulsion force due to the electromagnetic interactions, the charges of the protons. That is very nice. Since quarks are thought to be colored, at least theoretically, the theory that describes these very small particles that live in the quantum microuniverse is called quantum chromodynamics. Chromo for color, dynamics for the dynamics of these particles, and the quantum because this theory is a quantum theory. Very good so far, but this is not the only interaction. There is another interaction that these particles actually suffer, the weak nuclear force. Actually, I find this force very interesting because it is in the heart, in the core of the working mechanism of our sun and of all different stars that are across the universe. It starts as it goes on now. We have hydrogen, of course. The nucleus of hydrogen is just simply a proton that is composed of quarks. And quarks feel not only the strong force, but also the weak nuclear force. And then, if it is in the correct hot soup, like in the sun, this very nice, one of these very nice quarks transforms, and when it transforms due to weak nuclear interactions, it provokes that the proton becomes a neutron. Whenever it becomes a neutron, the neutron decides, just because of the strong force, to join another proton that was just passing by. They join together and they create a heavy nucleus of hydrogen called deuterium. And then they go around and they find another proton. They build together due to the strong force. They build together a nucleus of helium-3, and then they go on across the sun, find another helium-3, and when they combine together, they generate a lot of energy, an explosion of energy that liberates not only more protons, but also the light that we see with our eyes. And what happened there? Well, it all started with the weak nuclear force. In the beginning, it was a proton, and then it became, thanks to the weak nuclear force, to a neutron, starting this chain reaction that led to the energy that gave life on Earth. So for me, the weak nuclear interaction, of course, together with the strong force, is the source of life. So this is magnific. Now we know more about the origin of our life through the interactions of the most elementary particles that we have ever identified. But this is not the end of the story. We know already we have particles, we know these two forces, but of course there is electromagnetism, as I already said. They're responsible for most of our experiences, all these experiences we have had on Earth, and this is just electromagnetism. They're responsible to be just here talking to each other, might be actually mostly electromagnetism, but also the other forces. Okay, in the quantum universe of the elementary particles, these are the three quantum interactions: weak, strong, and electromagnetism. And we have all these particles nowadays. We have not only the two quarks that compose protons and neutrons, down and up here at the bottom of this table. We have some other 4 copies of these 2 quarks, and we have also the copies of the electron that is generically called a charged lepton. So we have the muon, the tau, we have in total 3 charged leptons, and there are some other partners, very light partners that I mentioned in the beginning that are called also neutrinos, that are also generated in the sun, that are also generated here on Earth in our reactors, in our nuclear reactors. All these 12 particles are the responsible of all the possible matter that we see across the universe. They live there, they build up everything, they build up us. That is very nice. And they interact, I told you, through the strong, weak, and electromagnetic interactions. But as I told you, in the strong interactions, there are these gluons that glue somehow together or are responsible together of building up structures like protons and neutrons by joining together different quarks. But also the other properties have certain particles, sorry, it's Spanish, I'm sorry, they should say leptons, quarks, and forces. And these are the particles on the right that are responsible for all the interactions. We have the gluons with a G, we have the photons for the interactions as mediators of the electromagnetic interactions, and we have also the weak gauge bosons, the gauge particles responsible for the weak interactions, the Z and the W gauge bosons. All of these particles are responsible for the 3 interactions that we have analyzed before. These are the 12 particles that are responsible for the composition of all the matter that we observe, and also the cosmic rays are composed out of these particles. But in the mathematics of this model, with all the particles that I have described, all of them are massless. But I told you that there are some particles that are heavier and some others that are lighter. So there must be a mechanism to give them mass. That is where the 2012 discovered Higgs boson enters into the game. The Higgs boson appears as a field, actually, first of all. This is a field that covers all the points of the space. And when the particles entered in the beginning of the cosmological history, this field, they acquired its mass. That's the reason. If the Higgs field didn't exist, then we wouldn't be able to see the masses of these particles. And of course, as every field in nature, as the electromagnetic fields as well, tiny perturbations of the fields generate the particles, the particle that was discovered in 2012, the Higgs boson itself. Okay, very good. Then we have 12 particles that have spin. They are spinning around. They have actually a very funny value of spin, but they are spinning around. We have the Higgs boson that is not spinning around at all as quantum particle. It doesn't spin. And we have also the responsible for the interactions that we say it has also a behavior as a vector, as an arrow in the cosmos, and it's an arrow that is spinning. These are all the particles that we know. So we have in total this 12, this 4, that makes 16, plus this one, 17 particles. They compose everything. Very good so far. Now we understand what the universe is made of, or maybe not. The point is, what about gravity? Everything feels gravity. Everything that has mass feels gravity. Einstein, Newton before Einstein, told us that. Einstein told us that gravity is due to the deformation of our space and time, of our 3 dimensions in time, and its evolution leads to gravity. Very good. But unfortunately, in the quantum world of the elementary particles, whenever you perform computations of gravity associated to these quantum particles, you obtain an error. Error is like, for example, in a pocket calculator, when you take it out and you divide 1 by 0, you obtain error. That is the kind of error that mathematicians called infinity. And infinities, or divergences, pop up everywhere in these quantum gravity computations when we deal with particles, and that is very bad. They are errors of the theory. We should solve them. How to solve them? Maybe the solution is that we have to understand better how to combine gravity with the other theory that was discovered by this fellow, another German fellow called Max Planck, who invented quantum mechanics, or gave the source of the invention of quantum mechanics. So we have 2 fathers of very revolutionary theories here, both of them Germans. The theories have to get married at a given point. Of course, they have to get married, but apparently it is not possible because gravity is excluded from the quantum universe. This romance cannot be. Not so far, unfortunately, unless string theory might be the solution. We don't know. Let us see. What is string theory? String theory is the theory invented by these 3 fellows I told you before. These 3 fellows thought of particles like just simply vibrational modes of a single string. Of a single string that is, I don't know, traveling everywhere, and whenever it vibrates too much, it becomes a very heavy particle. Of course, since our perspective or our experiments measure only very large distances, it could be that these strings are very, very small, and that's the reason why we cannot see the extended object. They are very small. They have the so-called Planck length that is like 10 to the minus 35 meters. I mean, this number is really, really, really small. The tiniest size that you can imagine is the so-called Planck scale. And these strings should have that size. Therefore, if they are vibrating, we cannot see it with our eyes. We cannot see it with our best experiments at LHC, for example. We cannot see the vibration, but it can be. It could be that it is true. But I told you before that it didn't work. It didn't describe the elementary particles that people were trying to figure out. It didn't describe the cosmic zoo. It did work, but we didn't realize very well what was happening. That is what people asked. Let's imagine this is the atom. Then in the center is the nucleus. The nucleus is composed of neutrons and protons. The proton is composed of 3 quarks. And these 3 quarks are really point-like particles. Are they really marbles? Or are they really just strings? Like this closed string that is vibrating there. Could it be that actually quark is that, but it looks like a marble or a point from our perspective because our eyes are too big, our experiments are too large? Could it be so? It could be. And not only that, besides strings, in string theories, there are some other extended objects. There are closed strings, as I showed you. There are these strings that are opened. And from these extended objects, this surface that I drew there, they eject from time to time, some closed strings that have all the properties of the hypothetical particle that might be responsible of the gravitational interactions, the so-called graviton. So one of those strings has all the properties that people have conjectured that the graviton should have. It has the proper amount of spin, it is massless, it mediates gravity as well. How come that we arrived at this? Well, the point is that they started with the strings like you imagine just simply a, I don't know, string, a thread, and then they quantized that theory. When they quantized the theory, that means that they try to understand it from the point of view of quantum mechanics. They noticed that the vibrations could be understood as all particles, like the perturbation of a given field, of a string field. And one of these particular vibrations looks like this. It has the correct amount of spin, it has the correct mass, it has the correct interactions, everything. It is a quantum graviton. Therefore, the string theory quantized by these fellows that I showed you before is a theory, a quantum theory of gravity. And people, of course, celebrate it. The hypothetical graviton is found in string theory. It's a closed string in string theory. That is very nice. Then it is a theory of quantum gravity. And if it is a theory of quantum gravity, you might be able actually to invoke all the other forces as well at this level and make a full theory of all the possible interactions and of all possible particles that I described before. Is it possible? That was the question. Unfortunately, when you have good news, you have also bad news. Unfortunately, it is almost always like this. This string theory has at least 3 issues that I would like to present here. Unfortunately, most of the strings resemble just simply gravitons and Higgs bosons. They look like that. They have to be gravitons or Higgs bosons, or, second problem, tachyons. And tachyons are really evil particles. Whenever you talk about tachyons, people actually remember those particles that travel faster than light. Some other think about imaginary particles with imaginary masses. Very funny. But actually, for people talking or working with particle physics, they talk about tachyons about, well, they regard tachyons as instabilities of the universe. Whenever a tachyon is present in their theory, it means that the theories are not stable, that our universe will decay, will get destroyed in a fraction of a second. Very fast, disappeared. A tachyon is not welcome. And there is a tachyon, a tachyonic boson in this theory that I just described before. Evil news. Third problem. This new nice theory with gravity inside contains or is valid, is mathematically valid without any errors, without any infinities in 26 dimensions. And we see 3 spatial dimensions, right? When we observe a box, we see 3 dimensions. And time, okay, the 4th dimension. We have only 4 dimensions, space-time in 3 + 1 observable dimensions. Where are the other 22? No, this theory cannot be right. But people working on this in the very beginning, the early 70s, they said, well, but it is a quantum theory of gravity. Come on, there should be a way to rescue this astonishing theory. Let's see whether it's possible. And they looked around in the news, in the papers written by scientists as well, and they noticed that there was a very nice idea. The idea was that it is possible that all these errors, these problems, come from the fact that all these strings have almost no spin except for the graviton. So what happens if we add spin? Let us see, let us give them a spin to see what happens. But how do we do that? In those days, there was a very popular theory that is still popular, by the way, among particle physicists, the so-called supersymmetry. By the way, Sheldon Cooper was doing supersymmetry until he realized that he should do superasymmetry. You saw maybe that episode. Well, this has to do somehow something with that. What is the supersymmetry? Particle physicists were thinking about the problems of the theory of particle physics, in particular the question why their masses is just what it is. They wanted to figure a reason. It cannot be that it's just simply like that because. No, it should be a reason. What is the reason? Probably the reason is that each particle has a copy in the mirror, a very heavy copy. So for the W boson on the right, there is a winner whose difference is only that whereas the W boson is more similar to the Higgs than to the matter particles, the winner, its upper partner, is more similar to the matter particle. It has the same spin, it has this, many properties similar to the leptons and quarks of the particle physics of this table with 17 particles. Very nice. And the same happens to the Z boson that mediates the weak interactions, or to the gluon, or to the photon. And it should happen as well to the electron and to the quarks. All of them have to have a superpartner. That's what they thought. And with that, they solved the problem. So the difference between the observed particles and the conceived hypothetical supersymmetric particles is precisely their spin and their mass as well, of course. But that is what they had in mind in order to solve one problem in particle physics. Then string theorists said, well, if the difference is spin, I can start with non-supersymmetric strings that are boring and have no spin, like this one on the left, and make it super. Let's add the super partner, the super string. The string has spin as well. And now let's combine them together. Let's put them together and see what happens. What happens is that the theory is forced to have strings of a very tiny size. I told you before, 10 to the minus 35 meters. That is a mistake. 10 to the minus 35 meters. Also, there is a graviton that is preserved, that quality is preserved. Certain strings look like photons. On top of the graviton and the Higgs, there are also photons and gluons that mediate the fundamental forces. That is very nice. Now we have all the interactions, and that is what people talk about when they say something about a theory of everything. This everything is arrogance, pure arrogance, of course, because everything, they are talking just about all the possible interactions, gravitational interactions, weak interactions, strong interactions, electromagnetic interactions. That's all what they are talking about. This is a theory of everything, in quotation marks, of course. But here I haven't said anything about the other particles. What about the quarks? What about the leptons? They are also there. Thanks to supersymmetry, they can also appear there. And an add-on, no tachyons, nor any other inconsistencies, nor divergences anywhere. I mean, the problem of quantum gravity, when you try to quantize gravity, just adding quantum mechanics to the theory of Einstein, that problem doesn't appear in this context in string theory with supersymmetry. And the resultant particles can, but must not, exhibit supersymmetry. So you can decide, depending on your model, depending on your favorite string theory, whether it has supersymmetry as particle physicists demand or not. That is very nice, because so far we haven't seen supersymmetry. It is still on the run. People say very frequently that that string theory predicts supersymmetry, and that is not true. Anyway, so these are the nice things that people observe about these strings. But whenever there are good news, there are bad news. There are 6 extra dimensions. 6. Of course, it is different from 22, and we're very glad that it's different from 22. Much smaller, very nice, but still 6 extra dimensions. A headache. I observe only 3 spatial dimensions and time. I mean, I observe only 4. Where are the other 6 extra spatial dimensions? Anyway, let's ignore that problem. Of course, that is not evil. Let's think for a second. That's what people thought in 1985. And they started classifying all the string theories that had those properties, good and bad properties that I showed before. And they come up with the idea that there are 6 different string theories. These 2 theories, type 2A and type 2B, with much much more supersymmetry than they conceived in the beginning. Actually, 2 copies. Instead of 1 mirror, they have 2 mirrors. For each string, they have 2 copies. To super partners, they have 2 supersymmetries. Type 1, it has only 1 copy, 1 supersymmetry. We have already 3 superstring theories. And what happens is we combine the old SIG string theory, the very first with 26 dimensions, with one of these superstring theories, and we make a hybrid. If we make a hybrid, we generate the 3 heterotic strings that are here and that are fully consistent. They are not SIG. They live in 10 dimensions and have all the other properties that I showed just in the previous slide. 1985, the first revolution of string theory, the birth of these 6 theories. But I showed you this scheme for a given reason. Let me tell you why. Very soon, they discovered that not only strings, as I told you before, were allowed in string theory, but also so-called branes. Branes are generalizations of membranes. Membranes, like in a drum, right? 2-dimensional membranes you play with, but you could have also 3-dimensional membranes, like a volume. 4-dimensional membranes, I cannot imagine that myself, but mathematicians can. 9-dimensional brains, they can imagine that as well within the core of this theory, and that this can exist. Indeed, in this particular theory, we might actually be living in a 3-dimensional membrane, in a 3-dimensional brain of this. Okay, we have brains, we have strings. How are they related? Actually, what they found in the 90s is that membranes, these brains that I drew in here and the strings that I drew before, are actually more connected than we think. Actually, we can transform a brain into string. They are actually together. But whenever you do something like that, mathematically, you go from one theory to the other. You go to one of these theories to some other theory. There are dualities. There are transformations that allow us to go from one theory to another by transforming strings and branes, by playing with the sizes of string and branes, by playing with the dimensions that are predicted in string theory, but only, and that is what this fellow showed us, Edward Witten, only if you allow an additional dimension. That is not only the 6 extra dimensions, but 7 extra dimensions. And you have there in 11 dimensions a new theory called M theory. I don't know what the M stands for, maybe model, membrane, matrix, nobody knows. People say that is Witten, but backwards or upside down, right? We don't actually know, and he never told us, or he doesn't want to tell us why he invented the M in M theory. But in M theory, all these theories build the happy elephant. Here, when everybody is looking at the different corners of the elephant is sad. But whenever you find these dualities, the elephant gets happy. We have a new theory, a new unified model of all the string theories. And if these theories describe also nature, particularly our particles and interactions, then a unified theory of all possible interactions, a truly theory of everything at this level. That's why people were so happy in 1985 and then in 1995 when the second superstring revolution started, people said. But as I said, it's valid in 11 dimensions, and that is a very, very evil problem. The same problem we had in 10 dimensions, we have it here, but just worse. And we observe just simply 3 spatial dimensions in time, 4 dimensions in nature. Does this theory describe actually nature? That is the question. People went back to the theories of 106 years ago. One idea, but Gunnar Nordström, this guy, imagined mathematically that our universe might have more than 3 spatial dimensions. Probably, why not? 4 spatial dimensions, 5 spatial dimensions, I don't know, 9, 10, 11, 10 or 11 spatial dimensions. He didn't care. He just simply proposed this idea. But of course, physicists have to try to deliver a theory that can be tested, where every description that has been done before can be built on. And that is what this fellow, Kaluza, did. He said, look, 4 years ago, Einstein came up with his theory of gravity in our 3+1 dimension. That is very nice. What happens if we accept the idea of Gunnar and accept one extra dimension, just one? Then let's make a theory of gravity. A theory of gravity in 4 dimensions. Here I just put a hypercube in 4 dimensions. Yeah. And he said, okay, let's put it like that. Analyze the theory of gravity using general relativity, but in 4 dimensions, spatial dimensions instead of 3 as Einstein, and see what happens. And he discovered that it is possible to split this theory into a theory of gravity in 3 dimensions as Einstein's theory, and in addition, in an additional theory that resembles electromagnetism. It's very similar to what classical electromagnetism looks like. So people were very glad in those days. Of course, whenever you have good news, there are bad news. He put his theory in a paper, he submitted his paper, and Einstein, of course, received the paper to study it and decide whether it was good or bad. And he said, he wrote in a letter to Kaluza, I have great respect for the beauty and boldness of your idea. He actually liked the theory, however, rejected. Yeah, good news and bad news. Of course, Kaluza was not very happy, but the reason why Einstein rejected this theory is because it couldn't be tested directly like that. I mean, he was supposing that there was a 4th dimension that nobody could observe. That is sick, that cannot be true. Paper rejected. Okay, very good. But then there was a fellow who asked this question, why don't we see the extra dimensions? Why? And he came up with an idea that I think is associated with his name. His name was Oscar Klein. For those of you who know German, Klein means small. And he came up with an idea to make the extra dimension, yeah, you guess, small. So he wanted to compactify the dimensions. Let's do it here. Let's do the idea, put in practice the idea of Oscar Klein to make small an extra dimension, to compactify it. Let's suppose that the vertical dimension of this picture, nice picture of a house in the US, is an extra dimension. Let's suppose that. So let's compactify it. I did. So in the beginning, whoops, we have 2 dimensions. Yeah, width and height. Okay, now let's compactify the height. I did it. So that is more or less, of course, I'm exaggerating a little bit, but that is the idea of Oscar Klein. We don't see the extra dimension because it's compact and it is small. That is what he said. And he talked to Kaluza, and they said, yeah, let's work together and build up a theory, the theory of Kaluza and Klein, the theory with extra compact dimensions. It didn't work actually at the end because, you know, electromagnetism is a quantum theory, and gravity, even in 4 dimensions, is not a quantum theory. Then you cannot arrive at a quantum theory from a classical just like that. You have to do something else. However, the idea is beautiful. How come? Look, this guy is walking on this line. This line is 1 dimensional. He only sees forward and backward. But what happens if you look at what they see, what the ants see, what these little small beings see? They see not only forward and backward, they see also around. They see an extra dimension. But this extra dimension is very small. It's something that the big fellow cannot see. He sees only forward and backward, but the ants can see more because they are small. If the extra dimensions are just like that, we could actually have extra dimensions in our universe. The extra dimension that proposed Kaluza or Gunnar might be actually around here. Not only that, the 7 extra dimensions of M theory, or the 6 extra dimension of all the different 6 string theories might exist. How come? Well, at every point of our universe, there might be a dimension, just compactify it in a circle, or if they are 6, compactify it on something else, in something that mathematicians called a manifold, a Calabi-Yau manifold, or any other space, in a cup, in a chair, or something, in a figure like this flower-like figure that I have here. Maybe in each point, if we were that small as tiny strings, we might be able to see that, to see the extra dimensions associated to each point in our space and time. That'd be great. Then probably the only thing I have to do is to take the 6 extra dimensions of the string theories of the 7 dimensions of M theory and compactify them a la Kaluza-Klein, perhaps. But if you do so, can you observe anything at all? I mean, they are very small. Let's suppose that you do. How can you test this theory? I told you that this is very essential. Kaluza-Klein said, you can test this theory. Even if you conceive just one extra dimension, these fellows told us that there could appear, due to the compactification, many copies of each elementary particle. The electron should have a copy, and the mass of the copy would be much higher due to the size of the extra dimension. If the size of the extra dimension was large, the mass could be light. But if the size of the extra dimension is small, then the extra particle, the particle twins, could be much heavier. And then they said, since I want these dimensions to be compact and small, otherwise we cannot explain why we don't observe them, then the masses of the particle twins will be larger than the masses of the particles that we observe. Let's look for them. Let's go to an experiment and look for them. Not only that, in the theory, if we accept that theory and we just can put a lot of energy within these extra dimensions, then we can create many black holes. We can accumulate a lot of energy within, an extra m there, sorry, accumulate a lot of energy in the extra dimensions, hide it somehow, and create many black holes. Of course, we might be in danger. People thought actually like 10 years ago, let's not create them. Let's not start the LHC because it will create many black holes and then they will suck up everything they find in their way. But fortunately, actually Hawking told us that if they are small, then they will evaporate very, very fast. The smaller they are, the faster they evaporate. That is very good news, because even if they create black holes at a collider, an accelerator, they will not destroy the accelerator, first of all, nor anything else. They will evaporate and they will be just simply left as missing energy because they will evaporate. It will be energy that will disappear within the extra dimensions. Then if you have a machine that generates tons of energy, a large amount of energy, you should be able to simply go and generate Kaluza-Klein twins or many black holes and detect them. That is what people are doing right now. This very moment, at least in Switzerland, the LHC, they are trying to detect these guys and they report every day. I haven't seen them. Sorry, I haven't seen them. Therefore, what is the conclusion? Well, there are two possible conclusions. The extra dimensions do not exist, or the other, they do exist, but they are smaller than the LHC can somehow measure. Let's see whether they can measure actually these guys. If they can measure these guys, then the idea of extra dimensions could be confirmed. And we could be very happy that, that this could be confirmed. But this couldn't confirm that string theory is a fact. It could confirm only that the extra dimensions exist. Then we have to go further. We have to investigate what happens in all the possible compactifications of string or M theory. What happens? It happens that all properties, the charges, the masses, the amount of particles, the particles probably responsible for dark matter and dark energy will appear from a string theory whenever you look at the details of the compactification. And that is what many people like me do. We try to look at all possible compactifications. There is a Klein bottle. Klein was a mathematician, of course. There is a sphere, there is a Möbius, there is a torus, there is a Calabi-Yau. There are many different shapes that you can compactify the extra dimensions in. And whenever you do so, you obtain different physics. Actually, people say different universes. And all of these universes are possible within the scope of string theory. So you might have many models that are very similar to the standard model, and then you have to decide which of them is the correct one. Which of them does not only match the properties of the particles and interactions that I described before, including gravity, of course, but also some other things where we have questions. Like I said, dark matter, dark energy, or many other particles that appear usually in these scenarios. Then whenever you predict a new particle within these constructions, you have to go directly to the experiment and test it. And that is what many people do. Try to use this string theory in order to predict the new particles and their new behaviors in order to be tested directly at the different colliders that are now on Earth. Very nice. But I told you that each of these models are equally probable in string theory, so that each of the universe described by these models is equally probable. Then we have this kind of scenario. I don't know whether you have watched The Matrix, but here they show a multiverse. Each screen shows a possible universe. Well, we have exactly that. We have the landscape of universe in string theories. In the compactifications of string theories, we arrive at that. And we have as many as 10 to the 500 different universes. We have a multiverse populated by an amount of possibilities that is huge. This idea is not only proper to string theory, it appears also in cosmology, it appears also in quantum mechanics. The multiverse exists in those theories, but we don't actually know whether it exists in the real universe or in the real multiverse. We really don't know. But it is a possibility and we have to explore it. Then there is another possibility that you have transitions from one universe to the other. And if that transition happens, then soon we might actually suffer a transformation of our universe. We have to measure as well that. How? Probably, for example, gravitational waves are more propense to suffer this transition like a quantum particle, that can just travel through a wall without performing a wall, without making a hole in the wall. Probably gravitational waves can travel between the universes of the multiverse, coming back at a given point, carrying traces of their experiences in the other universe. And that is one idea that people actually are pursuing today in order to save the day. Well, what do we have? People complain, you have many models, garbage. I don't care about your many models, your multiverse is just crap. They don't like it. I'm sorry for the C word. So you have many models in string theory. You start with a theory, you say, it's called M theory if you wish. You compactify your extra 7 dimensions, and then you get many models. But this is not different from many other theories, from general relativity or the quantum theory of fields that is contained within the standard description of particle physics. You have one theory, but then you write a lot of the solutions for the equations. Oh, again, I committed a mistake. Equation solutions. And then by analyzing these different solutions, you arrive at several models, and you select only the models that reproduce the real universe. And you call them standard model for a given reason. Of course, that has already happened. They arrived at this standard model, they obtain predictions, they confirm the predictions in 4 dimensions, and they are very glad. Of course, that happened only in quantum field theories. It didn't happen in string theory so far. We predict a lot of 4D constructions, 4D models, and we get certain predictions that unfortunately haven't been confirmed. So the confirmation, the standard model of string theory does not exist yet, but it might actually come very soon. So I started with a question. What is the universe made of? Well, we saw particles, 17 particles that appeared there, very nice. But probably this is not the end of the story, because we have many questions. Among them, what is dark energy? What is dark matter? Why we have the masses, or they have the masses they have? We don't know. In order to answer them, perhaps the solution is that our universe is probably made out of strings, and we have to deal with it. Then I will leave this here. Unfortunately, this is a criticism to string theory. We have string theory here on the left. Then something miraculous happens, and we arrived at the standard model of particle physics. We know more or less what we want to arrive to. We know what we want to start with, but we don't know what this miracle success is gonna be. We think there is compactification, and we want to be more explicit. But so far, we have been just as explicit as we can, and we cannot really trace the step between A and B. I hope that one of you, or maybe we all together, collaborate in order to get to the miracle. Thank you very much.
Thank you so much, Saul, for such a nice talk. So we have we're a little over time, but I also took quite a bit of your time. So
I'm sorry.
No, I took quite a bit of time. So I think we still have time for questions. I see a few that are already in the chat. I see Alex Cox. Maybe Alex, do you want to ask your question? Can we maybe let Alex speak? So let me, yeah, there you go.
Cool, thank you. So the imagery of a string kind of invokes the idea of a 1D object. I'm wondering if there's a local manifold near these strings, at least in theory, where the string itself is one-dimensional.
Basically, well, let me see whether I understood correctly your question. You're asking, given the one-dimensional property of the strings, you ask whether there is a manifold close to the string around which it might, I don't know, wrap up or something. Is that your question?
Yeah.
Yeah, basically the idea is that the manifold, we are living in a manifold, and the manifold has 6 extra dimensions that build up kind of a very nice shape, a very nice topology, a very nice geometry. It could be a clavijao, or it could be something different. There is also, of course, a manifold. And then the string, this one-dimensional object, goes around this manifold, enters that manifold, and sometimes when it finds some, I don't know, topological feature, it wraps around and stays there. Just simply stays there, the string. That can happen as well. So yeah, in string theory, that is a very strong possibility, and people actually use this possibility in order to describe the properties perturbatively or non-perturbatively that might lead to observations in our 4-dimensional universe.
Great. I see John Klink. Can we allow him to ask this question? Hi, John. Do you want to just go ahead and ask your question?
Yeah, sorry. I don't know how that ended up happening. I don't really have a question, but thank you for the seminar.
Thank you. I don't listen to you, Raul. You're mute.
Sorry. We have some questions in the chat. Let me go ahead and read some of these. So we had a question that perhaps we should have started for clarification. I think this was early on, so I think this question perhaps had been answered. But Trenton Frey was asking if you could clarify, what do you mean by a dimension?
Yeah, of course. Actually, I mean, let's suppose, well, let's start with what we observe. If you have a box, in order to determine the volume of this box, the size of this box, you have to measure 3 quantities: the depth, the width, and the height. That's it. If you want to locate an object in our planet or in our universe, usually you also use 3 coordinates: latitude, longitude, and I forgot, latitude, longitude, and altitude, of course. These 3 coordinates. These are the dimensions. If you have a 4-dimensional universe, then you need, in addition, 1 extra coordinate. I don't know what it could be called. Yeah, and if you want to measure the volume of this 4-dimensional object, this 4-dimensional box, you could need an extra number in order to determine its size as well. So this is how we say touch the extra dimensions. It could be a 4th or a 5th or a 6th number that you need in order to locate an object in that particular universe or to measure its size in that particular universe.
Okay, so I see another question from the beginning. Alberto Perez saying, hi, Saul and Reyes team, nice presentation. How do you think was the creative process of the scientific community around the Middle Ages? And how has that evolved through time?
Actually, I think that's a very tough question. There have been a lot of wars, there have been a lot of processes besides science that have happened. And in those days, those who were doing science actually were not, people just who had some other duties, some other jobs. They were rich people most of the time. They had time to think about it. And most of the scientists that we know of nowadays were brilliant scientists, but of course there were some others as well. There were a lot of alchemists, for example, that were making experiments trying to get gold. Their names, we don't know them because they didn't produce anything. They were every kind of person like nowadays there are. And what I think is that the thing that improved our comprehension of science and our behavior towards science is measurement. In those early days, they were just like testing, like a little child that is playing around and seeing or experimenting with everything he finds around, performing observations every day more carefully than yesterday, and at a given point, giving up because they have some other duties. But at a given point in the 19th century, in my perspective, they started performing experiments with measurements more carefully. They discovered chemistry in a very precise manner so that we can nowadays generate medicine, for example, or treatments for cancer, or communications and everything, thanks to the measurement. So this is a big step, I could say. From observation to measurement, there is a big step. It lasted at least like 300 or 400 years in order to get there. And nowadays, we arrived to a point where we are left with very tough problems. This is like somebody told me that story. We have a tree, you observe the apple, you grab the apple, you decide by observation and measurement whether it is rotten or not, and then you sell the apples that are not rotten, of course, and the others you plant them, of course, as well. That is very nice, and that is what happened, in my opinion, until the 19th century. But then the other apples that are just above there, that you cannot see very easily, we have to reach them as well. You have to invent ladders and methods in order to get there. And that is what we are doing right now. We are going to those precise apples that are very small, very complicated to grab, to see, to understand, to see whether they are rotten or not. We are there. And then we have to invent methods in order not to spoil them while we are inspecting them. We have to invent methods as well to use them because they are small and complicated. They might be useful for communications or not, we don't know. But we have to invent those methods, and we are there. I guess we are as clever as people were in the Middle Ages, but we have actually more difficult problems, but fortunately more tools.
That's great. So I think we have time for maybe a couple more questions. I see Peter Nicolas has his hand raised. Can we give him permission to.
Hi. Yeah, thank you. Yeah, I'm a huge fan of quantum theory, and I listen to Sean Carroll and a lot of your colleagues. But yeah, what is the difference between quantum gravity or graviton and gravity as we know it? I mean, obviously air friction probably doesn't have an effect. Yep.
Yeah, well, the first thing is that as Planck put it, whenever you go to very, very small distances, something like 10 to the minus 35 meters, all the interactions have exactly the same strength. So you might imagine that it doesn't matter. It doesn't matter that you have a quantum interaction, say electromagnetism, with the same strength as gravity, classical gravity, or say Einstein gravity without any problem. That is not a big deal. The point is that in order to realize how these communications between electromagnetism and gravity happened, you have to translate the quantum behavior of electromagnetism into the classical behavior of gravity. And this translation is only clear if you have a theory that describes gravity happening at those small scales or analogously at very high energies. In other words, if you can translate the quantum behavior of a small particles, this indeterminacy of the quantum physics, for example, this uncertainty principle in gravitational terms. In gravitational terms, the theory is completely deterministic. You can go to the moon without any problem. You can generate a GPS completely accurate. You do not have there the quantum behavior of gravity affecting your measurements. But we thought that at very small distances, you should be able to see also this undeterminacy. That is one of the key ingredients of quantum mechanics, and that is something that we don't see so far in quantum gravity. Another thing that happens in quantum field theories, it doesn't matter which, is that at a given point, the theories can be just simply made finite. That means that the theory does not lead to infinities. Whenever you have two particles, an electron and a photon, for example, they interact at a given point without producing anything weird. That doesn't happen with gravity. If you have a graviton, if you have the description of gravity by interacting, I don't know, those classical gravitons for a given second, and it hits a matter particle, instantly, it generates a boom of energy, divergences. So you have to deal with a quantum theory that does not lead to these divergences. So I have two small answers, two criteria to distinguish a classical theory of gravity against a quantum theory of gravity. The quantum theory of gravity has uncertainty, has the properties of the quantum world, affects very tiny particles, and behaves pretty much like all the other interactions. This is the first thing. And the second thing, true theory of gravity, of quantum gravity, does not lead to errors in the mathematics and probably even solves the problem of the singularities in black holes, for example.
Great. Okay, so we have time for one last question. Digonto, MD Islam, do you want to ask your question? Great.
Yeah, hello, hi.
Hi.
Very nice chat, very nice talk.
Thank you.
I had like two questions, but I don't know if like
you can ask them.
Okay, so first one is what are some of the effective models of string theory? And the second one is, so you talked about multiverses, and gravitational strings are the only ones that can travel between these multiverses, right? Oh, okay.
Not the only ones, not the only ones.
Okay, say they can travel. Can we differentiate between strings that are coming out from different universes? Or, I mean, how do you detect them?
Well, fast. The very first thing, what is the effective theory of string theory? More or less, that is the question, right? What does it look like?
Yeah.
Yeah, so the effective theory of any string theory compactification is a quantum field theory as far as we understand. A quantum field theory that includes in a semi-classical limit also classical relativity theory. So Einstein equations modified by some corrections that comes always in all string theory compactifications, modified by some corrections, and this leads to the second question actually, with some extra corrections to gravity that deforms the classic, well, the theory of relativity of Einstein's to give us certain signals that are not possible directly in a normal, in unusual relativity theory of gravity. In the quantum field theoretical scope without the semi-classical limit, we have more particles, more fields, and more interactions. And these extra interactions lead to something called dark radiation and also some other things called dark matter or dark energy in a very complicated fashion because they mix together with the observable particles. And we have hundreds of these extra particles interacting with the observable particles that we, well, the particles that we have observed so far in nature. So more or less, that is the scheme that we have in all the effective theories of string compactifications. And I told you, this goes to the second question, that we have extra phenomena or modifications to the description, to the equations of Einstein's gravity. And these modifications lead to certain gravitational effects that can be felt by every particle that we can measure, but affect strongly to the gravitational particles, those that lead to the gravitational waves. Basically, if we want to describe gravity as a quantum theory of gravity, the gravitational waves are just like the transit, the path left by a graviton, by a certain excited graviton, then it goes. But it is affected by these modifications by string theory. These modifications allow, among many other things, modifications within our universe, but also the transitions, the quantum transitions to some other universes. Whenever it goes to other universes, any field, in particular the field of a graviton, experiences certain modifications. These modifications can be kind of absorbed in the graviton, and if it comes back and it is detected as any other gravitational wave, then we should be able to measure all its properties in order to figure out whether it was modified or not. And if it was modified, we should be able, and that is something like a work in progress, we should be able to distinguish between the modifications that can happen in our universe from the modifications that can happen in a certain additional parallel universe that could happen, that could exist. Certainly this is a kind of, I must say just like that, everything in string theory is just conjectured. We really don't know, we don't have any test, experimental test to measure all of this, but we hope that the more precise the measurements of gravitational waves become, the better we can understand first the gravitons, and second of all, the better we can also understand whether or not the graviton is experiencing anything that is happening within our universe gravitationally or within other universes. And right now, people just simply put a lot of papers in our archives in order to show that they figure out a different scope, a different conjecture, a different idea in order to deal with this question.
Well, on that hopeful note about potential findings of the future, let me say once again, thank you so much to Saul for taking your time and sharing this really interesting talk.
Thank you.
Many of us, there's many more questions out there that were left unanswered, literally by our participants. But hopefully, you know, they've gotten a taste of what this field has for them. So let me just remind everybody that this is the beginning of a fall series. The next talk is going to be in October. It's going to be Jamie Sahorian. The next one is going to be Stuart Henderson, the JLab director. And then the last one is going to be a NASA astronaut. So please stay tuned, follow us on Facebook and social media, and register to REYES to keep getting informed. And go to our page, odu.edu/REYES. At the end of this talk, as you exit, you're going to have a survey generated, which we appreciate your feedback. This is a service that we're trying to provide for you. So please take your time and give as much feedback to us so that we know how to do our job better. Thank you, everybody. Thank you again, Saul.
I have just one very small question. In order just to answer some of your questions, you can write an email directly to me. I don't know whether I can present my slide with my email address so that people can copy it, and just simply send an email to me, and I will be very glad to try and answer your question if you wish. If you wish to pose it. So let me just go here, and this is my email address, ramos@physica.unam.mx. Please send me any question that you might have in mind. I couldn't like that you just simply left it with a question that was left in the chat here, and I didn't have time to answer. Please forward me your question. Thank you.
And Saul's slides will be available on our website as well as the video for this recording. So you're going to be able to see it again. So thank you so much, Saul. It's always a pleasure.
Pleasure has been mine, as always. Thank you, everybody.
Take care.
See ya.